Hello, this is step 2, 2007 question 14, the last question on the statistics part of the paper, where you're asked to consider a random variable x with this continuous probability density function, where it's 0 between for values of x less than or equal to 1, the natural log of x between 1 and k, the natural log of k between k and 2k, and a minus bx for between 2k and 4k, and 0 everywhere else. So this is a pretty easy graph to draw. If we just draw in our boundaries real quick, we're going to have a 0 there, a 1, k, 2k, 3k, and 4k. So it's quite obvious here that it starts at 0 for values of x less than 1, so that's just a straight line there. We don't have to draw it in because it is just the y-axis. For the natural log of x between 1 and k, the natural log of 1 is 0, so it does start at 0, and it ends somewhere off here at natural log of k, which would be around there, and it's a curve like that. So for between k and 2k, it's the natural log of k, and with respect to x, that is a constant, so that would be a straight line off to 2k. And since we have a continuous probability density function, this linear function a minus bx has to be equal to natural log of k at the beginning and 0 at the end, so that is just a straight line going from there to 0. For part 2, we're asked to determine a and b in terms of k and find numerical values of k, a, and b. So we can start off with what the connection we made in the first part, where a minus bx has to be equal to the natural log of k at x equals 2k and 0 at x equals 4k. So we can use that to make a system of two linear equations. So a minus b at 2k is equal to the natural log of k. That can be our first equation, and our second equation, a minus b at x equals 4k is equal to 0. So now we can just eliminate a from these equations. If we do equation 2 minus equation 1, we can take away these. We're going to get a minus b lots of 4k minus another minus b times 2k, which was going to be a plus, and then that's going to be 0 minus the natural log of k. So here we have negative 2k lots of b equals negative natural log of k, and we can just divide through to get b equals the natural log of k over 2k. And similarly, if we just plug in b into equation 2, we're going to get a minus the natural log of k over 2k multiplied by 4k equals 0. So these k's go, and this just becomes a 2 on the top, so we just get an a equals 2 times the natural log of k. So from then, we need to find the numerical values of k, a, and b. And to do that, we have to recall the definition of the area under the graph of a continuous probability density function, which is equal to 1. So we're going to use this equation here, that the integral from minus infinity to infinity of our continuous probability density function is equal to 1. So that gives us that this integral from 1 to k this part there from 1 to k of the natural log of x with respect to x is equal plus k times the natural log of k, which is this rectangle here. And then we're also going to have a rectangle which is a half times 2k times the natural log of k, which is this rectangle right there. So if we solve this, we're going to have, by integrating by parts, you're going to have x natural log of x minus x between k and 1 plus the whole thing from before. We can simplify this to k times the natural log of k. This is going to become k natural log of k minus k minus, in brackets, 1 times the natural log of 1, which is 0, minus 1 plus 2k natural log of k, which is equal to 1, and therefore we get that 3k times the natural log of k minus k plus 1 equals 1. And from here it's quite simple, you just cancel these ones, and then 3k times the natural log of k equals k, these k's cancel, and then natural log of k equals 1/3, and by raising both sides to e, we're going to have k equals e to the 1/3. That's our first numerical value. And if we remember that a was equal to 2 times the natural log of k, we get a equals 2 times the natural log of e to the 1/3. The natural log and the exponential function cancel, so we're going to get that a equals 2 times 1/3, which equals 2/3. And similarly we can do the same with b. b was the natural log of k over k 2k, which becomes e to the 1/3, the natural log of that, over 2 times e to the 1/3, which becomes 1/3 over 2e to the 1/3, which just simplifies to 1 over 6 e to the minus 1/3. For part 3, we're asked to find the median value of our probability density function x, which is going to be when the area under the graph is equal to 1/2. So that's going to happen either in the first region, the second region, or the third region. We can do those step by step to figure out which region the median is going to be in, and how that will work. So firstly we have to consider the integral from 1 to k of the natural log of x with respect to x, and that's equal to the integral from 1 to e to the 1/3 of the natural log of x dx, which we can see because in the last part we figured out that k equals e to the 1/3. So with this from the last part, we know that this integral is equal to x times the natural log of x minus x between e to the 1/3 and 1, and this will simplify out to just be 1/3 e to the 1/3 minus e to the 1/3 plus 1, and it's our job to figure out if this is bigger or smaller than 1/2. So this expression here is either going to be bigger or smaller than 1/2, and that's going to determine whether we look in this region or the next region alone. So we can prove this by this inequality here, which simplifies to this. So we can just divide by 3 over 2, which is going to get our inequality to become, if you divide by this, you flip, so it's bigger than 3 over 4, and then we can cube both sides to see that E is bigger than 27 over 64, which is true. So we look into the next region, this rectangular region here that I'm coloring in now. So to look into that, we're gonna have to look in between a midpoint and where our median value is probably gonna lie. And this is a rectangle, so we can figure the area of that out by m minus k times the natural log of k. So this area here would be equal to m minus e to the 1/3 multiplied by our natural log of k, which is 1/3. So we have to get this area and add it to the previous area to make it 1/2. So we have 1 minus 2/3 of e to the 1/3 plus 1/3 m minus 1/3 e to the 1/3 equals 1/2. So from this we can simplify it to get 1 minus e to the 1/3 if we bring these two terms together, plus 1/3 m equals 1/2, and from this we can just isolate m, so 1/3 m equals e to the 1/3 minus 1/2 if we take the 1 to the other side as well. So m would just be this times 3, which is 3e to the 1/3 minus 3 over 2, which is going to be our median of x is at x equals 3e to the 1/3 minus 3 over 2. Now we also have to check if our median is in between the range of our region from k to 2k to make sure it's within this rectangle here. So we have to make sure that this 3e to the 1/3 minus 3 over 2 is smaller than 2e to the 1/3, which we can rearrange this inequality to get e to the 1/3 is smaller than 3 over 2, which we can cube to say that e is smaller than 27 over 8, which is true. So that means the median of our continuous probability distribution function x is 3e to the 1/3 minus 3 over 2.